So firstly, myself, Saiyadali, PhD scholar from IIT Dharwad, from Karnataka, India. So here, I would just like to extend my thank to my supervisor, Dr. Somashekara, MA, for giving this opportunity to uh, explain or give presentation on a research topic pertaining to this examining mechanical, thermal, and shape memory properties of metastructures. So before entering to the main agenda of this presentation, just I would like to give my journey about IIT Dharwad, like where initially it is established in the year of 2016 by MHRD, Government of India, and then again since it is a growing institute, so a lot of research work has been started, and with R&D laboratories and again the SCI facilities and all. So and again the newly joined students are now residing at the permanent campus and all. So with this, I just quickly begin with my presentation outline, like where I'll be giving some brief introduction about the shape memory polymer and again the metastructure, followed by the literature and then methodology, and again followed by synthesis of PLA and TPU 20%. And again here results and discussion part, and finally summary and the future work. So to begin with, like as we all know, everybody what exactly the shape memory polymer and how exactly it works. So underlying mechanism of this SMP is that like when we just heat that particular SMP to above glass transition temperature, definitely it will chains will mobilize, and whatever the force we apply, of course, the extension or compression, it will be in at its temperature when we cooled it down. So if we want again, then the initial shape, definitely we will just if we heat that more than glass transition temperature, it will take back its initial shape. So this shape mechanism, again, we have basically taken a shape memory polymer based metastructure, like where we have selected a metastructure because of its good features like negative Poisson's ratio and energy absorbing capability and better damping capability. Right here, the metastructure, of course, having a great applications in various fields. Look, some among them has been depicted over here. So if we look into this, the work pertaining to this boat rendering systems, and which has again the gradient in itself, which has been arranged over there, and again, so one of the presenter has been already presented this particular work, which has they have metastructure gripper, which is very inspired, and nobody has basically worked. I mean, converted this metastructure to a gripper. So this is very inspiring for me, especially, and again this meta damping devices which will be used as this hourglass structure. But in my case, like I just took this metastructure in such a way that like there are some limitations in it. So if this figure definitely tells us one by one, like where each unit cell is not carrying uniform load, and again there is a Meena et al, like the work which is done by the Meena, like where they are basically the structure is collapsed in a row-wise manner, and again the work by Mukdam, so where these metastructures which are again hybrid and re-entrant and all. So here no, like the metastructures are deformed laterally. So by looking at these structures, we can able to look into this. So to mitigate this problem, so in our study, we have basically designed a structure in a such a way that like it will overcome all the problems. So where if we can look into this animation, which is again by the simulation we have done through Abacus. So here we have make sure that like at metastructure should take uniform loading, and again there is no lateral deformation and less concentration zones and all. So by considering this perspective, like we have basically done an inspection on this through a simulation. So by this way, we have selected this kind of geometry and the configuration as well. And here, quickly move to the methodology point of view. So like as I was telling about the selection of the metastructure, like we have basically make sure that like it has a particular feature which has been explained over, and then we move on to the material aspect, like where initially we worked on this PLA, and then we have this blended TPU of 20% by weight in this PLA, and again, and we have printed the metastructure of selected geometry, and then we are focusing or we are targeting the application here is that like the the pallet, which basically has a certain 4, 6, or 8 different numbers of legs, so where the people have used in a packaging industries and all, so which again basically will be having a good amount of load, and the repeatability is a major thing we just to need to look for. And with this, I just want to give more well, a brief about the synthesis of PLA, like how exactly it has been manufactured. So here we have just took granules of it, and then we have subjected that to high speed mixture, like where it will basically mix uniformly, and then we preheated the granules for certain hours, like at 80 degree, 50 degrees Celsius, and then we subjected that to extruding in it, and like where it is extruded and then subjected to condensing in it, and then we wind it through a spool, like which is having a 1.75 diameter. So then with this, I just want to enter into dive into the preliminary results. So like where we have synthesized this PLA-TPU and the PLA. So understanding its mechanical properties are most important. Like where if we are dealing with this simulation aspect, and then again other things. So to be precise, like of course this PLA is a brittle material, like which basically fails catastrophically. And since this TPU is a flexible nature, like definitely it will be having a soft failure, like it has a longer elongation break, like which has been depicted in this tensile behavior of it. But definitely in compression, no, like it has again the stress softening, and so due to the compression thing, so definitely it will load will the compressive strength will increase. So this is pertaining to this preliminary results of this and mechanical properties. So now understanding its thermal properties, like the how exactly this material behaves in variation with the temperature. So definitely this particular PLA and TPU varies with the temperature value. So where the storage modulus has been recorded for this PLA is of about 1.5 GPa, and then for PLA TPU is definitely very less compared to this PLA for the particular temperature. So then it again once it reaches that particular temperature, it suddenly drops. So that's what the structure looks like. And then this TG, of course, this tan delta will give us the particular TG value of this entire shape memory polymer, whatever we have used here. And we recorded around 67 and 69 approximately of this PLA and PLA TPU respectively. And in addition to this, again, just I wanted to quickly give overview about the experimental test, whatever we have done. So basically, we have selected a, 7 mm deflection. I can say the threshold deflections by having a iterative cycles. Like we just started with 5 mm, 7, 6, 6, 7, 8, 9, and 10. So we selected a 7 mm such a way that like basically this PLA, since it is a brittle, if we go more than threshold deflection, it will definitely fail, and we will never ever achieve proper repeatability, whatever we want. So in this case, so it has again the linear region, and again this flat region, which is again the load bearing structure, we can say. So for constant load, there is a for a constant load, there is a more number of displacement. So here, no, like the I can call in a term is that like the densification will be can be seen in this center cell, I can say the middle cells. So which is again these are the cells which are more prone to the load bearing capability. So now this observation is like which it shoots up, no, like where individual unit cells will penetrate into each other, and then reason for that is the main reason is that. And then so as I was discussing about the repeatability point of view, like here, no, like we have basically selected a deflection value in a such a way that like it has to be loaded or deflected for a constant strain to maintain that particular aspect. So we have basically set it for 11.75%, which basically approximately about 7 mm. So here, no, like since it is a polymer which is a brittle nature, PLA, so it deteriorates its load bearing capability. Even though it has a capability of shape recovery, it will recover, but there is a compromise in the load bearing capability. So with this, we basically tested our PLA TPU based structure. So here also we need to, I mean, we achieved, or we can say the same behavior, but one thing here to notice is that there is no crack initiation, rather than there is a white band formation can be seen. So there is no crack initiation can be seen over here. So with this, we have just extended our study to again the repeatability, which is more important. So we just tested it for 30 cycles, like where initially we load it and then unload it at room temperature, and then we apply it to constant water bath, like where it will be recover its shape. So with this, no, like after certain cycles, I can say after 10th cycle, it stabilizes and it will take good amount of load, and the load is very constant. And here after 30th cycle, like I mean to say, I can say at a 30th cycle, so the structure bit fails. So which is, again, I cannot say it is a fracture, but it fails definitely. And then there is no compromise in shape recovery behavior, as we can see this particular the bar graph. Next we extended this to again the 12 mm. So where, so we make sure that like at 7 mm it definitely works well, and then for 12 mm, how exactly it behaves key, like since the deformation, or I can say the percentage of deformation is very high, so metastructure get failed, which is being indicated over here. So this first figure indicates the after first cycle recovery, and this is the 10th cycle, 10th cycle unloading part. So here, no, like the metastructure of the individual in itself has been connected to some member, so which has been fractured. So by this we can say that like the metastructure is like took a very less load when compared to this 7 mm deflection. So by comparison part of view, just to keep with this in comparing with this PLA, definitely we can see this catastrophic failure after its 12 mm loading. So here the metastructure fail in this region, particular region, and again the metastructure here is like completely densification at its middle rows, I mean to say the second row and the third row. And here there is no proper like failure, or I can say the no fracture, but definitely there is a wide band formation, which is again the extended thing for the failure part of it. So for by summarizing the all my presentation, like here definitely we basically worked on the 7 mm deflection and 12 mm deflection, like where we could able to see here the PLA metastructure fails at fourth cycle, and it frequently disintegrates after few cycles, which is again the drawback of it. And then so definitely this PLA is in a brittle in nature, and it will take higher load, but here the less deflection. But in case of this PLA-TPU, the load is less, but the deformation we can go for a larger extent. So in this case, with this cyclic test, we basically came to know that like it has higher toughness and fracture resistance when we blend PLA with this some portion of, I mean, the composition of TPU. And so then with this we have some feature work also, which we are going to include in near future. So prediction of failure location by FEM approach. And then again, as we just went directly to 12th cycle, so we just wanted to test it for 10 mm also. So just to look for how exactly it behaves, and so its repeatability point of view, just we wanted to check. So yeah, so these are the references which has been excited for this particular presentation. And then so far, and I would like to thank Dr. Somashekara for giving some good insights in this project work. And then I would like to acknowledge the funding bodies, SERB, Department of Science and Technology, and then the Technology Translation Award, so from the SERB, and then Indian Knowledge System. And finally, I would like to thank this sophisticated central instrumentation facility at IIT Harvard, and then I would like to thank research mates, JTS, Mr. Ram Kishore, and then Vikash Kumar. So this, I just want to end my presentation. Thank you for your kind attention.